Right, so morning everyone. This is the revision lesson for the second physics, and remember that you're going to be doing an assessment on this next Friday. So that will be Friday the 30th of April. The bit that we're going to be looking at today is on momentum. And so what we've got down here are two videos which are excellent, which are going to talk about changes in momentum and conservation of momentum, the two sections that you need to have a think about. So these are the Cognito videos, and they can be really useful. I'll put the links on the Show My Homework so you can go directly into them along with the PowerPoints. So I'm going to start off with the idea of what momentum is, and the first thing that you need to understand is that any object that is moving is going to have momentum. So if we have a car moving down the road, if we have a person running, if we have someone on a bike or a skateboard that is moving, then we consider that that object has momentum. They all have different amounts of momentum, because that is determined by how fast they're traveling and the mass of that person or object, those kind of things put together. But they all have momentum as long as they are moving. And we can see that represented here. So we can see we've got velocity and a mass, and so momentum acts in this direction, the direction of the resultant force. So what that means, and this is really important, is that any object that is not moving, therefore does not have momentum. So a stationary car, a stationary person on a bike, a stationary object, a stationary book on a table has no momentum because it is not moving. We can think about momentum in a slightly different way of how difficult it is to slow something or to stop it. And so you can think here about if you had a professional rugby player run into you, that would be really difficult to stop as compared to maybe a horse jockey who's going to be much smaller and have a lower mass. So thinking about how hard something is to stop is a really useful way of thinking about what momentum is. So final bit around momentum is thinking about the fact that it is a vector quantity because it has size, i.e. it will be as a result of the velocity and mass working together, as we'll see in the equation in a moment. So there will be a certain number that is associated with it, a certain quantity, but then it also has a direction because the direction will be dependent on the velocity, so the direction that that object is moving in, that determines the direction of the momentum. So equation-wise, momentum is equal to mass times velocity. So nice simple equation, and the momentum is going to be measured in kilograms meter per second. The mass is in kilograms and the velocity is in meters per second. So we can simplify that down as being P equals mv, which as a triangle gives us this, with P, momentum up at the top, mass times velocity at the bottom. Of course, if we want to work out mass, then we know we need to do momentum by velocity. If we want to do velocity, then we do momentum by mass, and of course if we want to do momentum, it's mass times velocity. So here's our equation just written out for us at the top. So we're going to think about what the story is, what the relationship this equation is actually telling us, because there is a relationship between these variables, and we can see that if we were to change the mass or the velocity, that will have an impact on the momentum. So we want to understand what that is. So we're going to start off with this question here, and we're going to do a couple of calculations in order to work it out. So you might need a piece of paper and a calculator at this point, and just work out the momentum in each of these situations. So our first one is we've got a car of 100 kilograms, and that's going to be traveling forwards with a velocity of 2 meters per second. So the question is, what's the momentum of that? So of course we need to take the mass, which is 100 kilograms, and we're going to times it by the velocity, which is 2 meters per second. So 100 times 2 gives us 200 kilograms per meter per second. 200 kilograms meters per second. So we can say that the momentum of a car of 100 kilograms traveling forwards with a velocity of 2 meters per second is 200 kilograms meters per second. So we want to bear that in mind and see what happens when we change one of the components of that equation. So if we keep the mass the same, so we're still 100 kilograms, but we change the velocity to 4 meters per second, what's the momentum going to be? So of course here you should have picked up the fact that we're doing 100 times by 4. So that of course gives us 400 kilograms meters per second. So let's have a think about what's happened to the numbers. So what we changed was we changed the velocity. So we've gone from 2 to 4, and so we've of course doubled the velocity. What's happened to the momentum as a result? Well, the momentum has gone from 200 to 400, which is also doubled. So therefore, if we double the velocity, we double the momentum. So we could talk about this being a directly proportional relationship. So next we want to consider, well, what will happen if we were to change the mass? And so we're going to compare back to this first one again when it comes to that comparison. So we've gone from 100 kilograms up to 300 kilograms this time, but we've kept the velocity the same, so 2 meters per second. So calculate what the momentum is here. So 300 times by 2 will of course give us 600 kilograms per meters per second. So what did we do to the mass? We went from 100 to 300, so we tripled it. And what's happened to the velocity, the momentum? It's gone from 200 to 600, which of course is also tripled. So tripling the mass triples the momentum. So again, we can talk about there being that directly proportional relationship. So there are some quite nice calculations to do, but we can summarize this idea and this relationship we see as saying that the greater the mass or speed of an object, then the greater the momentum. And we can also say that actually the momentum is directly proportional to the mass and velocity that an object has. So where this begins to get a little bit more difficult is thinking about conservation of momentum. So conservation of momentum is exactly the same as conservation of mass or conservation of energy. All we're saying is that momentum that we calculate at the start, so before a collision or before an explosion, will be the same as at the end. So momentum cannot be lost. So the total momentum must be the same in a system at the start and at the end. And so we can represent that in this kind of phrasing where we talk about if it's a closed system, so the fact that momentum can't leave the area, then the momentum before an event will be equal to the momentum after an event. And so we're going to see that across the following examples in a minute. So simply as a sentence is momentum is conserved. Momentum stays the same. So what we're going to do is we're going to begin to think about this situation. So here we have two objects. Okay, so these are trolleys, and this trolley is stationary. So we know that if it's stationary, it's got no momentum, and this trolley is moving, and it's going to collide, and then both of the trolleys are going to move off after the collision. And so the question is we're going to work out what the momentum is before, and we know that the momentum has to be the same after, so that's going to allow us to work out a particular component. So what we've got, trolley A and trolley B both have a mass of 1 kilogram. This trolley is traveling at 3 meters per second. This trolley isn't moving, so 0 meters per second. So what we want to do is we want to work out the momentum of the system before. Now, of course, this has no momentum, so we can effectively ignore this. This trolley has a momentum of 1 kilogram times by 3 meters per second. So 1 times 3 is, of course, 3 kilograms meters per second. So that is the momentum of the system before the collision. Now what we can do is we can begin to think about the fact that this trolley is stationary, so 3 plus 0 is, of course, 0, so the total momentum is 3 kilograms meters per second. So that's before the collision, and so we know that the collision before, the momentum before has got to be the same as the momentum after. So we want to work out what the velocity is going to be of A and B joined together after the collision. So we know that the momentum is going to be the same as before, so it's got to be 3 kilograms meters per second, but now we've got 2 trolleys, so the mass has changed. So we're looking to calculate V, so we need to do momentum divided by mass. So we're going to do 3 kilograms meters per second divided by the mass of the 2 trolleys, which is 1 kilogram plus 1 kilogram, so 2 kilograms. So 3 divided by 2 kilograms gives us 1.5 meters per second. So we can see that the velocity of these two objects is half that of the original object because the mass has doubled. Okay, so we've got that inversely proportional relationship. As the mass is double after the collisions, velocity has halved. So we're going to have to go at doing the same thing, but this time we're going to collide with 2 of the B trolleys. So remember, the trolleys have got a mass of 1 kilogram each. We're going to do the same velocity that they're colliding at, so we want to work out what the resulting velocity of A and the 2 B's joined together is going to be after the system. So working it through again, the momentum of A was 1 kilogram times by 3, so 3 kilograms meters per second. Momentum of B, they're stationary, so it would be 2 kilograms times by 0, which is equal to 0 kilograms meters per second. So the total momentum, 3 plus 0, is equal to 3 kilograms meters per second. Then the momentum of A and B together has to be the same as the momentum of the system before the crash. So therefore we know that it's going to be conserved. So what we're going to do is we're going to do a momentum of 3 divided by the mass, and so we've got 1 kilogram here, we've got 1 kilogram here and 1 kilogram here, which is 3 kilograms, and so we're going to do 3 divided by 3, which is of course 1 meters per second. So tripling the mass means that the velocity is reduced by a factor of 3, is reduced by a third, so it's only going to be 1 meter per second. Inversely proportional relationship. So an explosion is just the reverse. Instead of colliding, they're going to be pushing apart. So here you've got this part of this trolley which is going to push both trolleys apart with the same force. And so what happens is when we hit this pin, it's going to push them apart. So trolley again is 1 kilogram, so both of these are a kilogram, and they are going to be, it's going to push off at 3 meters per second. So we need to work out what the velocity of B is going to be. So first job is to work out our momentum of A. So of course that's 3 times 1, which of course is 3 kilograms per meters per second. Now conservation of momentum tells us that the momentum of B must be the same as the momentum of A. So therefore B's momentum must equal 3 kilograms per meters per second. So we're going to do 3 divided by the mass, which is 1. So that means that we're going to have a velocity of 3 meters per second, because we're doing 3 divided by 1. So as the mass of the trolleys is equal, the velocity is going to be the same. So they're both going to be moving at 3 meters per second. And what that means is they're going to hit these barriers at exactly the same time because they're traveling at the same speed. Now, same situation as we did in our first example, we're going to have 2 trolleys joined together. So we've got 2 kilograms here and 1 kilogram here, and we're going to be pushing off at 3 meters per second. So we know our momentum of A is going to be 1 times by 3 kilograms meters per second. The momentum of B has to be the same, so it's going to be 3 kilograms meters per second, but divided by 2 kilograms, so 3 divided by 2, which is of course 1.5 meters per second of velocity. So this is going to be traveling twice as fast as this, which makes sense because this is 2 trolleys and this is only 1. So this will hit this side first in half the time that this takes to hit this one, or this is going to take double the time to hit this barrier because it's traveling half as fast as this one. So we can say as the mass is doubled, the velocity is halved, and therefore the double trolley is going to travel half the distance of the single trolley in a set time, or it's going to take double the amount of time to cover the same distance. Right. There are a load of exam questions for you to have a go at, and we're going to include the mark schemes for all of that on the Show My Homework that's going to have this on. And good luck. Come in and ask us any questions. Remember, you're going to be assessed on this on Friday, and on Monday you've got your biology assessment on homeostasis 1, and on Wednesday you've got your chemistry assessment on the chemical analysis section, so that kind of chromatography section that we've gone through. Good luck. I hope you have a good weekend, and we will see you next week. Thanks a lot.